Swayamprabha. Digital India. Educated India.
Today we will start with a new topic, lab on a CD. So the motivation behind studying this chapter is to talk about a microfluidic platform which is low cost and which can be used for many potential applications using medical diagnostics. So how does it look? Let me just try to show you that essentially how the product looks like. So this is a typical example where you have a disc. Now this disc has several channels. I mean the camera will not be able to capture all the channels, but this disc has several channels, radial channels, cross radial channels, and there are various holes which are like reservoirs. So through these holes you can inject samples of blood or other chemicals and there can be reactions taking place on this. So just like a big pathological lab, you can have all the activities like say for example mixing, reaction, valving, all these types of activities you can do on this disc. Now how will you actuate the fluid flow? You will actuate the fluid flow by rotating this disc, and that rotation will create some forces due to rotation. By virtue of these forces the fluid will start moving, and there will be some aiding forces, there will be some opposing forces, and as an interplay of all these forces the final motion of the fluid will be decided. So we will try to understand the fundamental science that goes behind this particular technology, and then I will try to demonstrate the fabrication process maybe through a small video, that how these devices are fabricated, and then we will talk about some research issues. I mean it is not that we will be resolving all the research issues, but I will just discuss that what are the important research issues that have been going on, and many of these discussions for many of these related discussions I acknowledge the support of Professor Mark Madhu of the University of California at Irvine, who has been our collaborator in this particular program, and with his strong and active support we have been able to establish the CD fabrication facility in our own lab. So with this little bit of note we will start with different microflows, a comparative study. So pressure driven flow, we will compare 4 types of actuation, not that these are only types of actuation: pressure driven, acoustic, electrokinetic and centrifugal. Pressure driven, acoustic, electrokinetic and centrifugal, out of this you will see that electrokinetic is a little bit different from the others, because in electrokinetic transport we will see later on the transport is strongly dependent on the chemistry of the sample, that is pH, concentration, all this. Now on the other hand the other mechanisms are not so much dependent on the chemistry or electrochemistry. Scaling of these forces, like pressure driven flow, the head loss scales with inversely as 4th power of the characteristic length scale for a given flow rate. For acoustic it is L square instead of L to the power 4, electrokinetic also L square, centrifugal quite intuitively it is also L to the power 4, because it essentially generates a pressure gradient by the driving rotational force. So it is it is another way of perceiving a pressure driven flow. But we have to keep in mind that when we are talking about the rotational forces, the rotationally actuated microfluidic platform, the channel may be of small size, but the rotational force may be strong enough so that inertial effects may be important. So we may not always trivially neglect inertial effects, just as we commonly do in low Reynolds number hydrodynamics. Flow rate in pressure driven flow, these are very typical. So one can get from nanoliter per second to even liter per second, but you know, I mean if you want to get flow rates as high as liter per second, you have to have very powerful driving actuation. Acoustics typically of the order of 10 microliter per second, and these are just orders of magnitude, rough idea. See, as practical engineers, see, I always wanted to, when I try to design this course, I always tried to make a balance between what is engineering practice and what is fundamental science. So if you make a balance between these two, then it becomes better and becomes easier for you to implement these ideas into practice. So electrokinetic flows typically 0.001 to 1 microliter per second. Centrifugal actuation, see the range of flow rate from less than 1 nanoliter per second to greater than 100 microliter per second. This wide range of flows can be covered, and you can understand very easily why, because I mean you can vary the rotational speed in a wide range, and if you vary the rotational speed in a wide range, you can vary the flow rate. The materials used for pressure driven flow, common materials are PDMS, polydimethyl siloxane, that is PDMS, plastic. For acoustic, the material used, acoustic actuation, the material used is commonly piezoelectric material. Electrokinetic, plastic, glass, PDMS. Centrifugal also commonly plastics and PDMS. Associated problems, pressure driven flow, dispersion, like I have discussed this earlier a little bit, that if you have a parabolic velocity profile, then it might be possible that if you want to achieve a reaction at the wall of a microchannel, then because of the big difference between the center line velocity and the wall velocity, what will happen is that the fluid will try to carry the sample along the center line, and the wall may be depleted, or the wall may be deprived, just in a very simple terms, the wall may be deprived of the sample which will react with the reactants present on the wall. Acoustic streaming is little bit an expensive process. Electrokinetic flows, we will see that like Joule heating is a very significant problem in electrokinetic flows, we will see later on. In centrifugal also, see, we are studying lab on a CD, but that does not mean that I mean there is always a tendency that whenever we are studying something, we always tend to talk about the positive points, but there are shortcomings associated. For example, if you want to have a very high throughput, what you will do? You will try to rotate the CD at a very high speed, and if you are rotating the CD at a very high speed, then there can be vibrations in the setup, and these are purely mechanical vibrations, and these vibrations can disturb the transport processes significantly. So as I told you that you have a motor on which you mount the CD, on which you have microchannels engraved, you can control the fluid flow by rotational speed and design of microchannels. See, you by looking into the CD that I had shown you, it is it will not appear to be made of a material which resembles with the CD that you use for external data storage in computer. It is just the shape, but if you can somehow combine the optics that you commonly use for the CD platform with the fluidics that you have in a rotational platform, then you can use this for detections of several things in a very smart optical environment. So it is possible that you can take the CD based microfluidics, I mean to a new level where you can combine optics with the rotational microfluidics. So rotationally actuated microfluidics. So I will start with a very simple example, then I will derive the governing equation for the rotational platform, but I will start with a very simple example. Let us say that just look at this picture. So there is a rotational disc, there is a rotating disc, and there is a fluid, and you can see that this fluid meniscus is such that the surface tension force in which direction it acts. Can you tell, is it radially inwards or outwards? It is radially inwards. Just draw the tangent to the interface, you see the tangent to the interface is inwards. So the surface tension force, so this is like a typical hydrophobic type of meniscus where the surface tension force is inwards, and when the disc starts spinning there is a centrifugal force which is acting on it, and that force is radially outwards. So there are two forces which are I mean there might be other forces, we will come into the picture, but these are two major forces. One is a surface tension force. Surface tension force might also be radially outwards, and if it is radially outwards then there is no control, that means then the fluid will spontaneously flow on the disc radially outwards. There is no need to have actually such a platform, because then surface tension will spontaneously drive the flow, but you can use it as a control mechanism when the surface tension is opposing the radially outward force. The radially outward force will increase beyond the critical angular speed, and it will increase sharply because it will scale with omega square or square of the rotational speed. So beyond the critical rotational speed what will happen, the centrifugal force will overcome the surface tension force, and at that speed the fluid will start moving. Why are we not bringing the viscous force in that analysis? The reason is simple, that the fluid has not yet started moving, we are thinking about the forces acting on it, and when the fluid has not yet started moving, viscous force has no role to play. Viscous force will start playing its role when the fluid had started moving. So we can understand from here that you can use this as a smart valve. The rotational speed can be used as a parameter to control the onset of flow. So only if you rotate the CD beyond the critical speed, then the flow will start, and that critical frequency, if the speed is omega, angular speed, then omega is equal to 2 pi f, that f is called as frequency, and the critical frequency at which the disc starts spinning, that is called as burst frequency. So we will try to see, we will try to establish that how we can derive an expression for the burst frequency. So the final result is given in the slide, but we will try to derive that by a very simple type of analysis. We will try to make more involved analysis as we progress in this particular lecture. So let us say that you have a micro channel, whatever channel, I mean it may not be micro channel, you have a channel which is rotating. So there is a big platform, and this is say one of the radial channels, right. So because of the rotation, so assume that there is a small fluid element of length dr, and width of the or area of the cross section of the channel is A. If it is of rectangular shape, then it is the width into height, but let us forget about the shape. Let us say that the cross sectional area of the channel, this cross section, this is A. Now when the disc is spinning, there are several forces, but we will first discuss about the interplay of the centrifugal force and the surface tension force, and then I will discuss that what are the other forces, and I will show you technologies where we have utilized the other forces to achieve some task. So in this kind of a situation, let the pressure here be P and the pressure here be P plus, P is a function of R only, say. So P plus dP, basically P plus dP dr into dr, okay. So the force is P into A, here P plus dP into A. So how do you estimate that what should be this pressure gradient when this disc is spinning? See, it is not necessary that you bring the surface tension force in the picture, because you have taken a small element where it is expected that on the both sides it will be neutralized. So when you are talking about the pressure distribution, what force you should bring in? Centrifugal force. So it depends on how you are looking into the problem. See, let us consider it from the fundamental mechanics point of view, okay. So when you are referring to a fundamental mechanics point of view, you can consider two types of reference frames. One reference frame which is inertial, one reference frame which is non-inertial. So if you are there watching the entire proceedings from an inertial reference frame, you will see no force, no question of centrifugal force. What you will simply see? You will simply see that there is an acceleration which is radially inwards, which is called as centripetal acceleration. However, if you are yourself sitting on the disc, which because of its rotation is a non-inertial reference frame, you will experience a force which is a pseudo force, and that pseudo force is called as centrifugal force. So I mean centrifugal force is one of the examples of such a pseudo force. So if we are, so what is the difference between these choices? When you are considering the inertia force, you can write the equations of static equilibrium by referring to the inertial force as a force. However, if you are considering the inertial reference frame, then the resultant force will be mass into acceleration. So in other words, if you are writing resultant force equal to mass into acceleration, that must be from a inertial reference frame, and there no question of inertial force. However, if you are writing resultant force equal to 0, it is as good as writing resultant force plus minus m into acceleration equal to 0. That minus m into acceleration is the inertial force, and here the acceleration is because of the centripetal, depends on how do you interpret it. If it is, it's a centripetal acceleration if you are talking in terms of acceleration. If you are talking in terms of inertial pseudo force by being located on the rotational reference frame, then that is manifested in the form of centrifugal force. So let us choose that second path. Yes, yes, pressure is inwards, right. Pressure is inwards, right, of course. So let us write the inertial force which is, so this, say this is the radially outward direction, So just to indicate that it is inertial force, I am drawing an arrow with I across it to mean that it is not actually an applied force, it is a pseudo force that is experienced because the observer is located on a non-inertial reference frame. Okay. So this is what, m omega square r, right. So m is rho a dr into omega square r, right. So all these forces must be balanced, that means P into A minus P plus dP into A minus rho A omega square r dr is equal to 0. So you have this is plus, right, plus, right, okay, this plus rho a omega square r dr equal to 0. So that means you have dP dr is equal to rho omega square r. So dP is equal to rho omega square r dr. Let us say that you are interested about a length of a capillary of finite dimension delta r, not a infinitesimally small dr but some finite dimension delta r. So let us say that this is 1, this is 2. So from 1 to 2 this is 1 to 2. So delta P is equal to what? P2 minus P1 is equal to rho omega square r2 square minus r1 square by 2. So rho omega square into r2 minus r1 is delta r into r2 plus r1 by 2, that is r average, right. So by rotational force what you are doing? You are actually inducing a pressure gradient. Now if this pressure gradient is sufficient to overcome the pressure gradient due to surface tension, then, and if the surface tension was opposing the radially outward flow, then the fluid will start moving radially outwards. So what is the pressure difference due to surface tension? Sigma cos theta into what is the total force? Sigma cos theta into perimeter, right. So in this particular chapter, in the slides also I have kept C as the perimeter. So the reason is many times we commonly confuse between the symbols of pressure and perimeter. So this is perimeter but we have used C as the symbol. So this is the force divided by area. So the fluid will start flowing when you have rho omega square delta r into r bar is greater than or equal to sigma cos theta into C by A. Right. omega is 2 pi f. So omega square is 4 pi square f square. So f is greater than equal to sigma cos theta c by pi square rho r bar delta r, 4 is also there, 4 then a, right, to the power half. So by this simple formula you can calculate that what is the expected speed at which the fluid will start moving, what is the expected rotational frequency of the disc. This is a very basic design parameter, right. You must know that what is the speed at which you should rotate the disc so that the fluid will start moving, otherwise you cannot do any fluidics with it. If you want to do a fluidics with it, you must first make sure that the fluid moves, and this is a very simple design consideration that can tell you that what is the so you can see that when the fluid is designed to move radially outwards depending on at what speed you start moving it. And why you want to have micro channels on the CD? You want to have micro channels on the CD because you are trying to utilize an interplay between the pressure differential due to the centrifugal force and the surface tension force, and surface tension is important only over small scales. So that is why you want to have micro channels on a CD, otherwise you could have ideally had large size channels on the CD, that would have made the fabrication maybe easier, but that will have the effect of surface tension less and less felt. So what you can do here is that you can make the CD acting like a smart centrifuge. So it is possible that depending on the rotational speed you can start a particular flow on a CD. So let us go to the slide. So that is what we had summarized, and the expression for the Bart's frequency. So you can see here that in the final expression Ford area by perimeter is written as the hydraulic diameter dH. So just an alternative way of expressing the same parameter. Possible applications, biochips, I have started with that example that you can use this CD as a platform for medical diagnostics, nano and micro scale water power systems, diagnostic devices, other optically powered nano machines in aqueous environments. I mean the like actually the CD is such a technology, like it's actually, I would say from my experience, that is like a giant undersleep. So if you make use of the CD as a technological platform, I mean there is no limit to which it can be exploited for microfluidics applications. And many of the applications in microfluidics where you can have a CD, I mean the challenge that it gives is that one is a technological challenge, and but the other is also a scientific pleasure, scientific challenge, that the science of fluid flow over such a rotational platform where microscale forces in addition to inertial force effects may be important, that it is a very rare combination that you get. Now question is, why do you use CD as a microfluidic platform? First, it is biocompatible. Biocompatible means you can use it for biological purposes. It is an effective substitute for standard consumables which you use in biological laboratory like slides, microwells, centrifuge tubes. These are very common consumables that you will find in biotechnological or biomedical applications, or even in pathological diagnostics applications. It is having versatility in handling a wide variety of sample types. Okay. So lots of different types of samples can be handled. Non-mechanical valving, ability to get the flow of liquids, just by controlling the rotational speed you can use the rotational speed as a valve. So you do not require a mechanical valve to control the flow. Simple rotational motor requirement. The motor that you commonly use for rotating this disc, I mean it can be a simple servo motor. So you can have a very simple motor by which you can rotate it. Economized fabrication method. I will say that this is one of the big advantages, that after we complete this chapter we will study the chapter on microfabrication, that how microchannels are fabricated, and we will see that there are many microfabrication processes which are very sophisticated, but they require expensive environment, expensively maintained environment. On the other hand, this lab on a CD is for making microchannels on a CD. You can use very simple apparatus, low cost apparatus in a very in a sort of quote unquote uncontrolled environment, an environment where the level of dust particles is not that strongly controlled. So for that purpose you can use simple mechanical manufacturing processes. Possibility of performing simultaneous and identical fluidic operations, and this point is like if you have a CD, on a CD you have many channels. So identical but simultaneous operations, on each channel you can do one thing. For example, if you think of a CD with 100 channels, then if you take one blood sample, one small drop of blood, in each of these channels you can make one test. So technically by using one drop of blood simultaneously with a single rotation of the disc you can make 100 pathological tests. So that is a very unique advantage of this. So for making the fluid flow through different channels you do not have to use different actuation, a single actuation will be able to transmit flow in all channels. Features of centrifugal actuation. See, the actuation is centrifugal, but once the fluid flow gets actuated, other forces in a rotational platform come into the picture, and I will show what are the other forces which come into the picture. Flow rates ranging from less than 10 nanoliter per second to greater than 100 microliter per second. Pumping is relatively insensitive to physico-chemical properties, which I have mentioned, that it does not depend on pH, ionic strength or chemical composition. In electrokinetic flows there are many advantages, but this is one point. I mean this may be actually used as an advantage, but it is sometimes very tricky because it is sensitively dependent on the pH of the solution in electrokinetic flows, but in centrifugal fluidics you do not require that. Different solvents, surfactants, biological fluids like blood, milk, urine have been pumped successfully, already these have been technologically established. Miniaturization and multiplexing easily implementable, so that means you can make microchannels on the CD quite easily, and you can do multiple you can study multiple reactions on the same CD platform, which is like called multiplexing. A whole range of fluidic functions including valving, decanting, calibration, mixing, metering, sample splitting, separation, I mean what and what not can be implemented on this same platform. So it is just like another form of lab on a chip. Instead of the chip you have the CD, and analytical measurements may be electrochemical, fluorescent or absorption based, and informatics embedded on the same disk could provide test specific information.